I want to introduce our next speaker, also coming in remotely, Laurel Genzoli from the University of Montana. Laurel, take it away, please. All right, we're seeing your screen. And
are you seeing my screen or my PowerPoint?
We're seeing your screen with the PowerPoint, but not quite in full screen mode yet. And we're seeing your notes view. Always the fun challenges. There we go. That looks great.
Okay. Awesome. Thanks, Randy. Oops, actually, give me just a second. Let's see if I can move our faces out of the way. Okay. So I'm going to give everybody an update on some work that I last reported on in 2019 at the Fall 2019 KBMP meeting. And so we now have 4 years of data looking at longitudinal trends in rooted aquatic plants and filamentous algae in the Klamath River below Yreka Dam. And this is going to be a project that's going to be contributing to some of the work that Desiree just reported on. So that was a great setup. Thanks, Desiree. So this project was initiated as part of my PhD work at the University of Montana and Flathead Lake Biological Station, but it's been supported by the Klamath Tribal Water Quality Consortium over the last 4 years to be able to continue these surveys. And there's been a ton of help in the design of the surveys, in the reporting, and a whole lot of help in the field over the last 4 years. So I really appreciate all the folks that have contributed. So as Desiree mentioned, algae is good, it's essential, but too much of it can be a problem. Algae and aquatic plants are essential to river ecosystems. They're a major part of the fuel for river food webs. They process and hold on to nutrients, they provide habitat. But when you have really high rates of algae and aquatic plants and high amounts of biomass, it can really degrade river ecosystems. It can cause water quality issues, and it can create a huge nuisance for fishing, swimming, and other water contact. And often these high rates of production are associated with species that produce toxins. And in the Klamath River, we have really high productivity throughout the basin that leads to water quality impairment. And so in the upper basin, we see these dense blooms of planktonic algae and cyanobacteria. And in the free-flowing sections of river, including the 190 miles of pretty high-energy river below Iron Gate Dam, we get a lot of species that are attached to the river substrate, and we get this buildup of biomass of filamentous algae and aquatic plants in the river in these free-flowing sections. And again, throughout the basin, this leads to water quality impairment and really limits people's ability to contact and use these waterways in the summertime. So in terms of how the Klamath compares to other rivers, the Klamath is among some of the most productive streams measured in the United States. This graph is showing daily rates of primary productivity on the x-axis, with the blue dots showing summer days at Syad Valley, and the gray dots in the background are daily data from other rivers throughout the United States. And then on the y-axis is respiration. And really what I want you to notice is that most rivers are falling out in this pretty low gross primary productivity, that's what GPP stands for, zone with a range of ecosystem respiration, or ER. But the Klamath in the summer is almost entirely in this mid to very high range for productivity. And again, just higher than most other rivers that have been measured to date. So we know that light and nutrients really control rates of primary productivity, but scour by high flows and sediment, like Desiree was talking about, can really set the organisms that are going to be present in a river. And those organisms are mediating how light and nutrients are processed, and then how you actually end up with these rates of photosynthesis and biomass of algae and aquatic plants in the river. And so we have these like basic understandings of how biomass accumulates and productivity ends up, but we really don't have a really good idea about how these different controls are going to interact with dam removal, because we know dam removal is going to affect nutrients. It's going to affect light to the benthic zone by influencing turbidity in the river, and it's going to affect scour. But there could be a lot of different directionality. And I think just in general, our hypotheses and understanding are still not super strong in terms of how the dam removal can influence biomass and also rates of production in the free-flowing river below the dams. So we have some questions that kind of overlap with some questions that Desiree was mentioning, but I'm going to actually show you some of the baseline data we have so far to address these questions. The first one is, how will the aquatic primary producer assemblages below the dams change with dam removal? And here we're expecting that these rooted aquatic plants, these vascular plants in the river, are going to decrease following dam removal because of increased winter scour, but that filamentous algae will respond more to turbidity and nutrient changes. And we're kind of lacking directionality still on what we're expecting there. I'm also asking, how will changes to primary producer assemblages change patterns of rates of primary production following the dam removal? So here I'm starting to get into this idea that when you have a lot of rooted aquatic plants, we're going to see different patterns of production in the summer. Specifically, I'm expecting more stable rates, higher rates of production, and earlier production where you have a lot of actual vascular plants compared to algae-dominated reaches. And this is in part just due to the life history characteristics of aquatic plants versus algae. Okay, so to get at these questions, we've been surveying the benthic habitat of the Klamath River for cover of rooted aquatic plants and filamentous algae for the last 4 years to get a baseline. We started this in 2019 with the expectation that dam removal would be happening in the next year or two, and we've been able to continue these surveys over the last 4 years, which in a minute I'm going to show you why that's been a really fortunate thing. So we have 10 reaches that we survey each year, and we use a mix of both wading in the more shallow habitat and snorkeling where it gets deep. We conduct these surveys once every summer in late July and June as base flow, as the river is approaching base flow levels. So our sites span from below Yreka Dam to above the Klamath River Estuary, with sites placed a little bit more densely between the I-5 bridge and Happy Camp area, and then more spaced out further downriver. We accessed each reach, which was around 1 kilometer to 4 kilometers long based on access, by kayak. And we did this so that we could really access transects throughout the river and make sure we're hitting a really representative range of habitat types. So we have 6 transects in each of our reaches. We split those transects into 11 evenly spaced quadrants, and we're surveying the benthic substrate of each of those quadrants. So we end up surveying up to 66 quadrants per sampling reach. And at each of those quadrants, we collect the percent cover of filamentous algae and rooted aquatic plants. We note the taxa down to genus for filamentous algae and species for the plants. And we're also taking note of the substrate composition in the quadrant. All right, so I'm going to jump right into some results here. We have a really strong pattern, longitudinal pattern, where we see that rooted aquatic plants decrease downstream of Iron Gate Dam. And so Iron Gate Dam, or sites closest to the dam, are on the left side of this plot. And as you get to the right, you're looking further downstream, and you can see that there's a consistent decrease in aquatic plants dropping off. But we also see that rooted aquatic plants had different amounts of cover from year to year. They increased from the beginning of our surveys in 2019 up until the most recent surveys in 2022. And so in this plot here, 2019 is the purple line, lowest, showing the lowest cover. And you can see there was a pretty consistent increase from 2019 to 2021, where it kind of stabilized or was similar between 2021 and 2022. And we think that this has to do with, there we go. We think this has to do with the lack of scouring flows in the past 3 years. So you can see I have just the maximum annual discharge plotted here on the y-axis, and then these are the 3 gauge sites on the main stem of the Klamath. And you can see that there was like a decently large flushing flow in 2019, but that maximum annual winter flow has been decreasing steadily since 2019. So we really haven't had a big scour event of a magnitude that would probably be able to really wash out and reset the plant community. Also, just a quick note that the increase in plant cover was really driven by two species, the two most dominant species in the river, which were Elodea and the curly leaf pondweed that some of you may know as Potamogeton crispus. And so the first year, the increase in cover was driven almost entirely by Elodea. And then in the second year, from 2020 to 2021, that increase in cover was almost entirely driven by curly leaf pondweed. So there's some interesting stuff going on in the biology of these plants that I don't understand, but would be really cool if somebody wanted to dive into that a little bit more. All right, I'm going to shift gears now to talking about filamentous algae cover. And we don't see as clean of patterns with filamentous algae in our surveys as we did with rooted aquatic macrophytes, but we do see that it tends to be highest in cover downriver between Happy Camp and Witchpeck. But the interannual variation is likely due to an issue with survey timing, where some years we're capturing patterns in algae when it's growing and really like vibrant and fresh, and other years we're catching it after it's already senesced. So we're catching less coverage because we surveyed too late. And so there could be more work done here to better capture patterns in filamentous algae. One thing our surveys really do capture, though, is a difference in dominant taxa of algae upriver versus downriver. These plots are for the 4 years of the survey, and they're just showing the percent cover by genus of algae. And you can see that at the upriver sites on the left of this graph, from I-5 to Syad Valley, we tend to see Eulothrix dominating, which is in this left picture here. And then downstream of Syad Valley, you get almost entire dominance by Cladophora. And so there are some trends here just in terms of who's succeeding, who's dominating that have fallen out in our data. All right, so I'm going to shift gears just a little bit here and address the second question, or start to address the second question that I mentioned early on, which is how does the assemblage of algae and aquatic plants influence patterns, seasonal patterns in daily rates of primary production in the river? So I went into this thinking that there's going to be these just dramatically different patterns depending on if algae or filamentous plants were dominant in the river. But we actually saw pretty weak correlations between total summer rates of production and maximum summer production between these algae and these plant sites. We did see some correlation with aquatic plants in that aquatic plant dominated sites tended to have earlier peak primary production, and there was less day-to-day variation in the production. But we also looked at patterns in respiration and the balance of respiration to production. And we have some interesting correlations here where sites that had more filamentous algae actually had less overall ecosystem respiration. So these highest algae sites, which are shown on the right side of the plot, had the least amount, this is a negative flux, so it had the least amount of respiration, which caused the most positive balance of respiration, or of production to respiration, or net ecosystem production. And the opposite pattern is true with macrophyte sites. When you have high coverage of macrophytes over on the right side of this plot, you end up having a lot of respiration as well at those sites, and that drives your balance of production to respiration into negative territory. And I started looking at the time series of the data here. And so these are two plots of daily primary production, which is shown as positive numbers in blue, ecosystem respiration shown as negative numbers in brown, and then this gray line is the balance between production and respiration. And at these sites with rooted aquatic plant dominance, we see this mid-season shift where initially you have positive rates of net ecosystem production, but they shift negative later in the summer. Whereas at filamentous algae dominated sites, we have positive net ecosystem production being maintained throughout the summer. And One idea behind this is that it might not actually be the algae or macrophytes that are really driving this change, but the macrophytes might actually be grabbing sediments, these carbon-rich, easily respired sediments out of the water column and maybe causing those to be respired within the reach. And this is an idea, just a little diagram showing how macrophytes can trap sediments, and then once they're trapped, could potentially be respiring those. Okay, so just to wrap up here, got some conclusions and considerations for future study. I think the first big takeaway is that rooted aquatic plants were highest below the dams, and they were also appear to be affected by winter scour, or I should say lack of winter scour. So I think this really solidifies that our hypotheses around what's going to happen to macrophytes are pretty strong hypotheses. And I'm also really grateful that we have this range of water conditions that we've been able to document the current condition of the river to compare with the dam removal condition. Unfortunately, Desiree also mentioned this, but I really think that higher frequency sampling is needed to better understand what's driving filamentous algae growth, especially Cladophora, and thus allow us to be able to understand how dam removal might change these growth patterns. And then finally, summer production was really similar overall between rooted aquatic plant and filamentous algae sites, but there were these really interesting patterns in respiration and the balance of production to respiration between these different community structures. And so I think that if we can kind of expand our ideas of how these different communities will affect production and respiration in the river, we'll be able to better predict and study the changes not only to the community composition, but also to the overall rates and ecosystem processes, which are really what's affecting things like dissolved oxygen and pH and nutrient spiraling in the river. And with that, I'm happy to take any questions if there's any time left.
All right. Thanks, Laurel. Thank you, Laurel. If there's any questions in the room, you can come up to the microphone. I see there is some chat happening. Let's see. Okay. Looks like Maya has the range of GPP and our respiration shown in the first graph for other rivers been screened to align with rivers that are similar to the Klamath in terms of nutrients, climate, seasonal flows, dams, etc. Or are they Great Aughts representing a very broad range of rivers?
Yeah, so right now this is a pretty broad range of rivers. These are taken from a USGS led project looking at 365 rivers from around the United States. They were screened for data accuracy, and the one thing I can say is that the rivers that had better data accuracy tended to be larger rivers with slightly higher rates of production, because small creeks with high gas exchange are harder to model. But yeah, they are across an entire range of rivers across the United States. So I don't think the Klamath is completely off the charts. Like, there are other high productivity, high biomass rivers that the Klamath definitely falls out along with.
Okay, and then kind of a follow-up from Maya also, is the biomass associated with rooted aquatic plants not sufficient to account for the higher observed restoration rates? Hence the thought about organic sediment trapping and associated respiration.
Yeah, so what I presented in this was the biomass. And so it is comparing the biomass of aquatic plants versus right, so that's what I'm correlating. So I guess I'm not sure how the biomass specifically, I don't know if you can clarify.
Yeah, sorry, I was just thinking, like, what led you to that thought about the organic sediment trapping, and instead of just saying, oh, well, it's the macrophytes that are respiring more compared to the filamentous algae. I was just trying to understand why you went there in the first place. It's totally interesting, but I wasn't sure why.
Yeah, I mean, I think in part because there's a general idea that biomass doesn't always equate outright rates of productivity anyways. And with macrophytes, especially, like, they're growing up, they're establishing, and then they're kind of just sitting there. Even a lot of the production in the system is likely coming from epiphytes, like diatoms that are growing on top of the macrophytes, especially later in the season once that biomass is established. So I guess this is a conversation I've had with quite a few people that have suggested that. I don't think it's necessarily all one or all the other. And I do agree that it could be some the actual organisms that are respiring, but yeah, I guess there's a lot of things that could be going on for sure. So it could be partly the organism as well.
Thanks, Laurel.
All right. And there's a few more questions here from Allison O'Dowd at Cal Poly Humboldt. How do you expect the longitudinal patterns to change downstream of Iron Gate Dam after dam removal? That's for the GPP rooted macrophytes and filamentous algae.
Which longitudinal patterns, Alice?
Yes.
So yeah, longitudinal from Iron Gate Dam, down to the mouth.
Yeah, I mean, I think in terms of the macrophytes, I still would expect if we have macrophytes retained in the system that there would be some longitudinal pattern, because obviously there's like a natural kind of longitudinal gradient as well. The dam essentially like increases the impact of less scour, but naturally scour is also increasing with these large tributaries that bring in more and more sediment as you move downstream. So if anything, I think that some of that pattern of macrophytes will probably be retained. I don't really feel comfortable making like strong suggestions on how the filamentous algae will shift still, just because we just have a lot of work to do still to understand why and even exactly what's happening with the filamentous algae.
And I would expect some short-term changes, would be different than long-term changes once the, sediment reaches a bit of an equilibrium. So. Yeah, definitely.
There's going to be like a disturbance effect initially. If turbidity is really high in the first year or two, we're probably going to see overall just really low rates of production in the river, because turbid rivers just don't have high production. You have to have light reaching the benthic zone to have high production. So that's like just a major control. But exactly, Randy, as it clears up, I think then we're going to start to see the influence of nutrients more strongly again, and some of the other things that are controlling the algae.
Yeah, and then a question from Megan Skinner: are nutrient concentrations correlated with vegetative cover as well, in a similar way as with flow?
I haven't directly correlated nutrient concentrations and benthic cover, but we're getting into that work, which I'll probably have something to report on within a year or so, looking at nutrients and actually rates of productivity over a longer time series. In general, it's been really challenging to show direct correlations with benthic algae and aquatic plants and water column nutrients, because a lot of the nutrients that are used by benthic organisms are taken up, in the case of macrophytes, from sediments in the nutrient or groundwater nutrients. And so yeah, I don't know yet, but it's not like a slam dunk trying to connect nutrient concentrations to benthic organisms because of these different sources of nutrients and where and how we're monitoring these things differently.
Another challenging question. Well, Laurel, thank you so much. That was great.